Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this set of videos we're going to introduce linear regression. In this video we're going to talk about what a regression is and then run our first regression. So far in this course we've covered a lot of different topics connected to microeconomics, but I have just given you things like demand functions, cost functions, and so forth. In the field we aren't typically given these equations, so we're going to need to estimate them. Regression is going to be our tool to do that. The field of studying economic data with statistical methods is called econometrics. My goal here is just to give you a quick introduction to econometrics and apply it to some of the problems that we will see in managerial econ. For right now, we're going to focus on using regression as a descriptive tool to talk about the relationship between two variables. We're not going to talk about causality yet. That's going to come later. Our goal with a regression is to estimate what we call a DGP, or data generating process. The DGP is an equation that describes the relationship between variables. Generically, we're going to write a DGP as y equals f of x plus epsilon. Let's break this down. Y is what we call the dependent variable. F of x is the determining function. The determining function tells us the relationship between our x, which we call the explanatory variables, and our y, which is the dependent variable. X could just be one variable, or it could be lots of different variables. We'll look at both cases as we move forward. The explanatory variables are observable variables that we can collect data on. Finally, we have epsilon, which is what we call the error term. The error term consists of the sum total of all of the unobservable factors on our dependent variable. So in summary, f of x, our determining function, tells us the relationship between the observable explanatory variables and y, and epsilon, the error term, is the effect of the unobservables. Moving forward, we are going to assume a linear form for our determining function, which means it's going to look something like this. Y equals beta naught plus beta 1 x plus epsilon. Just looking at our determining function part here, this is a linear relationship. The betas in this equation are constants. They're just numbers. The betas are what we call population parameters. These are unknown numbers that describe the relationship between x and y. The population refers to the whole universe of possible observations that we could get. For example, we might think about the entire population of the United States, hundreds of millions of people. If we somehow had access to data on every single one of those people, we could run a regression and determine what beta naught and beta 1 are with no problem. Unfortunately, that's not usually practical. We're going to have to do the next best thing, which is to collect a sample. A sample is simply a subset of the population that we have some access to. The ideal way to collect a sample is to do it randomly. By random selection, we mean that every member of the population has an equal chance of being selected. When we talk about a sample, the number of observations in the sample is n, also known as the sample size. I will consistently use a capital N to refer to the sample size for our entire time talking about regression. We'll use I to denote an individual observation within the sample. So I can be 1, 2, 3, and so on all the way up to n. If I is 1, that's our first member of the sample. I is 2, that's our second member of the sample, and so on. When we talk about our dependent variable y and our explanatory variable x, if I have no subscript on there, I'm just talking about the variable generally. If we have an I subscript, we're talking about a specific value of that variable for a specific observation within the sample. So for example, observation 3 within the sample would have a value of y3 and x3. Once we have a sample, then we're ready to run a regression. A regression uses our data sample to select estimates for beta naught and beta 1. When we use the word estimate in a regression, we are not talking about just making a guess. There is a specific mathematical method that's going to select those estimates based on the data that we have. To distinguish the estimates from the population parameters, we're going to use a special notation, beta naught hat and beta 1 hat. The hat on top of those just indicates we're talking about the estimates we got from the regression as opposed to the actual population parameters that we're trying to estimate. This is going to give us an estimated equation y hat equals beta naught hat plus beta 1 hat x. Y hat are predicted values of y based on our estimated equation and plugging in the values for x. Let's illustrate this concept using a graph. I'm going to draw two axes with x and y on each. On the left, I'm going to draw the graph for the population, and on the right, I'm going to draw a graph for the sample. Over here in the population, we have our line that is our determining function. This line is beta naught plus beta 1x. Note that there's no hats on either of these betas. This is the true line that exists in the population. It has an intercept of beta naught, and it has a slope of beta 1. What happens with this is that we get lots of different points that are in a cloud around this line. These points do not lie exactly on this line. What happens is we take a value for x, plug it into this equation, and then on top of that we add epsilon. That's our error term, the effect of the unobservables. So the distance for any of these particular green dots, that's an epsilon. That's another epsilon. They can be positive, they can be negative, but they average out to 0 so that that red line cuts right through the middle of the green points. Remember that the population is too big for us to realistically measure. We have too many of these green dots, so we are going to select from those green dots a sample. So all of the blue dots that I'm drawing over here on the sample side are also green dots on the population side. It's just that we don't have all of them. We're then going to run a regression that's going to give us estimates for beta 1 and beta naught. That's going to be our beta hats. So this line right here, this is our y hat line, which is beta naught hat plus beta 1 hat x. It has an intercept of beta naught hat, and it has a slope of beta 1 hat. The red line is the one that we are trying to estimate. The orange line is our estimate. Notice that they are not exactly the same, although they look fairly similar. The bigger our sample size, that is, the more of the green dots that we can get over on the right as blue dots, the closer the orange line is going to look to the red line. What we've done so far is called a simple regression or a bivariate regression because it just has two variables, y and x. Later on, we're going to talk about multiple regressions where there are more than one x. For our example, we are going to estimate a demand function. QXD equals beta naught plus beta 1 px plus epsilon. This is a linear demand function very similar to the ones we've worked with earlier in the course. Due to the law of demand, we would expect beta 1 to be negative, but we'll find that out soon. Suppose our client is a restaurant owner who wants to know the demand function for one of their products. The next step would be to go and collect a data sample of other restaurants with their price and quantity, and then run the regression. Here in Excel, we've got our data set. We've got quantity of good X, we've got the price of good X, and then we've got two other variables, the price of Y, a different good, and M, which is consumer income. For right now, we're just going to use our quantity and price of X. The first thing that we want to do before running a regression in Excel is to make sure we have the data analysis tool pack enabled. To do this, we're going to go over to File, and then click the button that says Options, select Add-ins, and then Go. Make sure that there is a check mark next to Analysis Tool Pack, and then click OK. Once we've done this, we can go over to the Data tab in the Excel ribbon, and there should be a button over here on the right-hand side that says data analysis. We're going to click that button. We get a few different options here, but we are interested in regression. Select that, click OK. We now need to select all the data that we need for the regression. Remember that y is our dependent variable. That's the variable on the left-hand side. In our example, that is the quantity of x. So we're going to select this entire column. I'm using Control-Shift down arrow to select the entire thing. Next, we want to select our x. That's our explanatory variable, in this case, price. I'll start right here and then use Control-Shift down to select the entire column. Note that I have selected the top row, which has our variable names in it. Because of that, we need to select the box that says Labels, and what that will do is make sure that Excel does not use that top row, which does not have any numbers in it. For right now, we don't need any of these other options, so we're just going to click OK to run the regression. Once we do that, we get our regression output. The numbers we're interested in right now are these two right here. Where it says intercept, that is our beta naught hat, and where it says px, that is our beta 1 hat. A common mistake is for people to say that px is negative 9.5, but that's not the case. Remember that price can't be negative, that doesn't make sense. Negative 9.5 is the coefficient estimate that sits next to the price of x in the equation. What we can do with these numbers is plug them into our estimated equation. Remember that the estimates that we're trying to get are quantity hat equals beta naught hat plus beta 1 hat px. The numbers we got in Excel are our beta hats. So our estimated equation is going to be q hat equals 4,279.4 minus 9.52 px. And this looks like a demand function like we've been used to working with. We could then plug in any price and predict what the quantity demanded would be. So for example, suppose the price of x was 200. We would then just plug that in and we would get 4,279.4 minus 9.52 times 200, and then the answer that comes out would be our prediction. It's very tempting to just plug this in right now and do the math, and you'd get an answer that was pretty close. The problem with doing that is that we just rounded, but we want to avoid rounding as much as possible. So to do this, we are going to go back to Excel and do the calculation there. Back over here in Excel, we are going to create a formula to figure out our predicted demand when the price is 200. We're always going to want to use cell references as much as possible to avoid rounding. If I click on this cell right here, you can see that we have a huge number of decimal places that are hiding inside that cell, and we want to take advantage of that. So instead of just typing in 4,279.4, we are going to refer directly to that cell by pressing equals and then clicking directly on that cell, and that's going to pull that number right into our formula. Next, we need to have minus 9.5 times 200. Again, we are going to take the negative 9.5 directly from the regression output table, so I'm going to do plus this cell right here, and of course plus a negative number is going to be minus, so we're all good there, and then multiply that by 200, because that is the price that we're interested in. And that's going to tell us our prediction for the quantity demanded, which is going to be about 2,376. Going back to the graph here, we can see that our predicted y hats, which are represented by the orange line on the right-hand graph, do not perfectly predict the actual y's, which we can see because those blue dots do not all sit along the orange line. For any given x, sometimes our prediction is above the actual value, and sometimes our prediction is below the actual value. The amount which the prediction was off is what we call the residual. We use E to denote the residual. We denote the residual for each observation as EI. Remember that each of these blue dots in the sample is a different I. For each observation, EI is defined as YI, the actual value of I, minus YI hat, the predicted value based on our estimated equation, represented by the orange line on the graph. Using our estimates, YI hat is defined as beta naught hat plus beta 1 hat xi. We take the x value for I and plug that into our estimated equation. Combining these two equations, we have EI equals yi minus beta naught hat plus beta 1 hat xi. And then distributing the negative sign, we have yi minus beta naught hat minus beta 1 hat xi. Looking at this on the graph, suppose that we had xi right here. The corresponding yi would be the height of that corresponding blue dot, and then yi hat would be the corresponding height of the prediction at that point. We would get that by just plugging in whatever the value is for xi into our estimated equation. The difference between those two is going to be our EI. In this case, the residual is going to be negative because the prediction was above the actual value, but just as often it's going to be positive. These residuals are going to average out to 0. Next, we're going to go over to Excel and calculate the residuals. What I'm going to do is just take our estimates and copy and paste those back over onto our original datasheet. I'm going to make an entire column of y hats, or in our case, qx hat. And so remember, that's going to be intercept. And I'm going to use F4 just to make sure we get those dollar signs in there. That ensures that our formula will hold steady on that cell. Then plus our slope term. Again, I'm going to use F4 to add some dollar signs there, times the price. That's going to give us our predicted value in this first cell for the price of 164, and then I'm going to fill in that formula all the way down. To get our residual, which we call E, we're going to take the actual dependent variable value and subtract the predicted one, and then carry that formula all the way down. You can see here that some of these are positive, some of these are negative. But one property of these is that they always average out to 0, which we can show using the average formula. And you can see that we get this number that is very, very, very tiny, basically 0. Another way that we can easily calculate the residuals is by going back to our regression. So we're going to go back to data, data analysis, regression. We're going to keep everything the same, but we're now just going to select this box that says residuals and run the regression again. And you can see here that Excel will automatically generate a column of residuals for us, and those match up perfectly with the ones that we just calculated. That's how we run a regression in Excel. In the next video, we're going to take a look at what's going on under the hood.